Utkarsh, call everyone.
Yes, ma'am.
It's 10:38 now.
Ma'am, I have put the message on the group. Everyone will join soon.
Okay, okay.
Good morning. Today,
Good morning.
Good morning, ma'am.
the next distribution, that is chi-square, and we have only F-test is remaining. Once we done with F-test, then the last unit will be over. I'll provide you the questions based on that so that you can just go and try to solve those. Okay, so let us see the chi-square test, and as I said yesterday, that chi-square variable, how you define it, it is a normal variate z square, correct? So it is x minus mu by sigma bracket square, and that variate is called as chi-square variate, and that variate is used for the distribution where we are assuming that it is a normal distribution, okay, for the sample size is greater than 30. So, so we have seen the test such as T test, F test, Z test, and they are all based on the assumption that the samples were drawn from normal distributed population. Or more accurately, what we can say that the sample means were normally distributed, correct? Now the testing procedure, it requires the assumption about the type of population or the parameters. So what we do is the population values, in this case, we call it as, these are all parametric test. Okay, so this test, T test is there, F test is there, or we have Z test. All the tests are based on the parametric one. So they are called as a parametric test. They are having called as parametric test. Now, in some situations, like it is not possible to make any rigid assumption about the distribution of population from which the sample is drawn. So the limitation is giving you the another alternative technique, and that alternative technique is nothing but the non-parametric test. Non-parametric test. That means no assumption about the parameters of the population, or the population we draw it from the sample. So here that test, the chi-square test, is called as non-parametric. Have any rigid assumption about the population. Like for T test, F test, we are assuming that it is normally distributed, and due to this understanding, we are having the population parameter is decided, and with this we are saying that they are parametric test. Whereas in chi-square distribution, the sample is too large. Okay, sample is too large, and there is no assumption about the parameter of the population. So these are called as non-parametric test. Okay, non-parametric test, and this was actually it was first discovered by Carl Pearson. Okay, so the scientist who discovered this, his name is Carl Pearson. And he discovered this test in 1990. He discovered it in 1990. So this chi-square test is a non-parametric test, and we are going to see the chi-square test of independence and the goodness of fit, and that is everywhere. Generally we are using this. Okay, everywhere generally we are using this. So this quantity is actually chi-square that describes the magnitude of the discrepancy between the theoretical value and the observed value. So we have seen yesterday that chi-square, in that case, we defined it as, chi-square is defined it as, it is summation of OI minus EI bracket square divided by EI for I is equal to 1 to n, correct? For I equal to 1 to n, and the degree of freedom in this case is n. Degree of freedom is nothing but the number of observations, and that is going to be n in this case. Okay, so we'll see the procedure now for solving or for checking the test of goodness to fit the chi-square distribution. Okay, so the procedure, test for goodness to fit chi-square distribution, to fit chi-square distribution. So we just take, in this case, what we do is we compare, in this case, compare the expected value and the observed value correct. That means the theoretical one and the practical one, experimental one, observed value. So take H naught, okay. So what we say that there is no significant difference, correct? There is no significant difference between EI and OI. EI means expected one and OI means it is observed one for I is equal to 1 to n. So here what we are doing is we are just taking the values. So I just take here instead of this because n is nothing but the number of observations and we are going to talk about the, okay, let it be. Okay, so EI and OI. So suppose here O1 to ON, O1, O2, ON are the set of observed frequencies and E1, E2 dot En be the set of expected frequencies, with the set of expected frequencies such that summation of I is equal to 1 to n of OI is nothing but capital N, and that is equal to summation of I is equal to 1 to n of EI, where capital N is summation of F. So you can see that the sample size for both of them is same, correct? So like I'm taking the data set for say 50 students in the class. So the expected marks and the observed marks, correct? So those are two totally different, or it may be similar, correct? So the data set for 50 students is going to be same. So here the sample size is same, correct? So that summation of OI and summation of EI is same, and that is equal to the summation of F. P is equal to the number of parameters estimated for fitting the probability distribution, probability distribution. So in some cases we may use, okay, for getting that experimental data, we may use the fitting of some of the distributions, like I can use Poisson distribution, I can use normal distribution with some parameters, correct? So then you are taking that as a parameter. Okay, that is one parameter. So calculate chi-square is equal to summation of OI minus EI bracket square by EI for I equal to 1 to n. So this we have to calculate. So if H naught is true, then Then the statistic, then the chi-square statistic, okay, that is this value chi-square is equal to summation of y minus ei bracket square by ei, okay, has as chi-square distribution with n minus p minus 1 degree of freedom. Now again, for chi-square distribution, we have a tabular data. Okay, tabular values are given with the degree of freedom, and that they have got the result after taking the survey of say ample of data sets. Okay, two big data sets, and then the conclusion has made. So that data we already have it with degree of freedom. Now here normally we have seen that in t-test we are taking the degree of freedom for one sample set, correct? It is n minus 1, correct? But here what we have is we are including the parameter. Now for your syllabus there's no parameter. Parameter is always going to be 0. So here we'll have that n minus p minus 1 as a degree of freedom. N minus p minus 1 as degree of freedom. So when it is true, when the tabular value, okay, so the tabular value is of course it is less than, tabular value has to be less than, it is the calculated tabular value has to be greater than the this one, correct? So I'm just saying in an opposite way. So H0 is true, H0 is true and accepted if chi-square calculated, I just write it down like this, okay? Chi-square calculated is less than chi-square with the degree of freedom is k minus p minus 1 with alpha, where alpha is the level of significance, correct? Level of significance. So we reject H0 when we reject, of course it is greater, correct? So here we are going to accept it when it is less than equal to also. In that case, for that level of significance, we accept the result, otherwise we reject it. Okay, otherwise we reject it. So for this, we take the examples, and these two examples will give you the entire idea of these questions. Okay. So let us take the first example. A nationalized bank, utilizes 4 teller windows, to the customers on a particular day, 800 customers were observed. They were given service. At the different windows as follows. As follows. So window number and expected number of customers. So that is 1, 2, 3, 4 windows are there. For the first window, it is 150. For the second window, it is 250. For the third window, it is 170. And for the fourth window, it is 230. The question is, test whether the customers are uniformly distributed over the windows. And what is given? Chi3 square at 0.05, that is 7.815. So here the degree of freedom, see, it is 3, correct? Degree of freedom is 3, chi-square 3, it is given. So you can understand that the parameter is 0 because the value of n is what? 4. How many observations are there? 4. And what is our degree of freedom? It is n minus p minus 1, correct? So n minus 1 itself, 4 minus 1 is 3. So p has to be 0. So here p is 0, correct? Now what is given? The question is given that there are 4 teller windows and 800 customers on a particular day they visited that bank. Okay, and then the expected number means what? They have already experimental data, so that we have it. But then what they want is test whether the data is uniformly distributed or not under this test. Okay, under this test. So we are using here the data set is, you can see the sample is very big. It is 800 given, correct? We are using here the chi-square test. Now, of course, the answer is not going to be correct. So here we have to reject. We are going to reject this hypothesis. You can say that that is not possible, correct, in real life. So what we'll do is, what we are going to do in this case is the expected number of frequencies are given to you here. So we have to take the hypothesis H0 in this case. So what is our H0? So the H0 is the customers are uniformly distributed. Correct? So this is the H0. So of course the H1, that is the alternative hypothesis in this case, is going to be the customers are not uniformly distributed. Correct? Not uniformly distributed. So what we are having is our objective in this case. So this is your window number, correct? Here the expected values are given. So the values of EIs are given. We have 1, 2, 3, and 4. Okay. So if you take the total number, okay, total summation of EI, it has to be 800. Correct? What are the values given? It is 150. It is expected number of, that means it is observed data, correct? So what is expected is we want uniformly distributed. So this is the value of OI, and it is 150, 250, 170, 230, correct? So this is our observed data. Now, what is your EI? What is expected? We want it to be uniformly distributed. So 800 by 4. So what I get this as 200. So 200 customers must be at one window, correct? So here the observed is this and the expected is uniform distribution. So you can see here that summation of EI is also 800. Okay. So in this case, you can see that summation of OI is equal to capital N, that is equal to summation of EI. Summation of EI. Now what we'll do is we'll calculate here. So here the parameter P is 0. So here P is 0. The value of N is 4. So the degree of freedom is going to be, it is equal to N minus P minus 1, that is 3. Correct? Degree of freedom is 3. Now I have to calculate chi-square as summation of OI minus EI bracket square divided by EI. Correct? So we'll take the first value. So first value is what? 150 minus 200 bracket square divided by 200 plus second value is what? It is 250 minus 200 bracket square divided by 200 plus the third value is 170 minus 200 bracket square by 200 plus, now here we are fortunate enough that we have all the expected values as same. In some cases it won't be same, so I'm writing it separately. So it is what? 230 minus 200 bracket square divided by 200. So you calculate this answer. Calculate it. What is this value? You can make the denominator as 200. The numerator is nothing but 50 square. 50 square. Here we have again 50 square. Here it is 30 square. Here it is again 30 square. Because negative also becomes positive. So what will be the answer? What is the answer in this case? What is the answer? Can anybody tell me?
I'm 34.
Huh?
Ma'am, 34.
34?
Yes, ma'am.
So we are getting the answer as 34. Now you can see that what is chi-square given for degree of freedom. See, this value is what? At 5% level of significance. It's 7.815 and we are getting the higher value, correct? We are getting this as greater than chi-square of 3 at 0.05 and that value is what? 7.815. Okay. So this is greater. So therefore reject H0. Reject H0. Okay. That is, it is not possible to distribute uniformly the customers. Correct. Reject this H0. So if the value, tabular value is lesser than the calculated one, you are going to reject it. You're going to reject it. So see, the problems are very simple. What we have to do is, the only thing is we need to calculate in this case the expected value, correct? The observed data will be provided it to you. That means the experimental data is provided it to you. The only thing is you find it out the expected values. And once you get that, you have to find it out chi-square calculated. And the tabular value will be provided. Okay, tabular one will be provided. Just you have to check the answer, compare the answer. And based on that, you have to accept or reject the hypothesis. So we take the next example. We take the next example. Among 64 offsprings of a certain cross between guinea pigs, 34 were red, 10 were black, and 20 were white, According to the genetic model, according to the genetic model, these numbers should be in the ratio 9:3:4. 9:3:4. Are the data consistent with the model at 5% level of significance? 5% level of significance, where the value for this is given as chi-square 2 at 0.05, tabular one, it is 5.99. Now see, the expected value is what? It has to be in the ratio 9:3:4. Okay, 9:3:4. But what is given? They have given that the observed one is 34 were red, 10 were black, and 20 were white. Correct? 20 were white. So what we'll do is here, first of all, I'll calculate the summation of F, that is capital N. So we have 34 plus 10 plus 20. So this is nothing but 64. Correct? Now what I want is, I want to calculate the observed and the expected ones. So what is observed? So for observed, I want here this data for the red, correct? For red, then the second one is what? Black and white, correct? Black and white. So observed is what? 34, 10 and 20, correct? So the summation of OIs is 64. Now the expected one, what I want it to be expected, they must be in the ratio 9:3:4, correct? So what we do is, actually we have here the value of N is 64, correct? Out of 64, we want this to be, see what is the addition of this, 9 plus 3 plus 4, 4 plus 3, 7. So this is 16, correct? So I want this to be out of 16, 9, correct? So here it is what? 9/16 into 64, correct? The total number of guinea pigs. So the sample is for 64 such. And then you want it in this ratio. So it is 9/16 into 64. So you can see that this is 36, correct? 16 4s are 64. Then the second one is what? It is 3/3 16 into 64. This is going to be 12. And the third one is in the ratio 4 by 16 into 64, correct? So it is 16. So you can see here that summation of EI, it must match, okay? So this is 6 plus 6, 12, 12 plus 2, that is 14, and then 64, correct? So this data should match. That is also very important. So you have to divide it and then later on you must check, because sometimes what happens is we may get the answer in terms of real numbers, correct? And then what we do is we just convert it in round numbers. And when you convert it in round numbers, then in that case, the summation can be different, correct? So that we don't want, So what we do is we just take the summation. Now what I have to do is for chi-square distribution, you have to take the observed minus EI. So you have to remember this formula. Correct. So for I is equal to 1 to 3. Now what is here? You can see here, this gives you the idea that parameter is 0. So here degree of freedom, that is D dot F, is n minus p minus 1, which is 3 minus 0 minus 1, that is 2. Correct? Normally we write degree of freedom, the entire words, but then we can also use the shortcut of this as D dot F, correct? Now you substitute the values. So the first value is 34 minus 36 bracket square divided by 36. Now you can see here the values are different, correct? In earlier case it was all expected values were same, but here it is different. Then the second one is what? 10 minus 12 bracket square divided by 12, plus the third one is what? 16, 20 minus 16. That is one and the same thing, because minus square is plus only, okay, divided by 16. So calculate this answer and tell me what is the value. Calculate this answer and tell me. So what's the answer? Can anybody tell me? Yes.
Ma'am, 1.44.
Okay, 1.24.
It's 44.
44. Okay. 1.44. Now you can see that this calculated one is this is 5.99, no? So it is less than this chi-square at degree of freedom 2 with 5% level of significance. So the calculated one is less than the tabular value. So here except H0, correct? Except the hypothesis. So that means we can So the data is consistent with this model, correct? Data is consistent with this model. And what is that model? It is in the ratio of springs are in the ratio 9:3:4, correct? So see, the questions are very easy to do it, okay? So I'll share some more questions based on it so that you solve those, and we'll see the F-test and the geometric and exponential distributions in the next week. So next week we'll finish with our syllabus, okay? And we'll have a test based on this on Friday. I'll keep your test, okay? So next Friday, I'm giving you 8 days for this. So in this 8 days, you will have a test on this distributions and the probability distribution, all the distributions, okay? So all will include not only Poisson, binomial and normal, will include all the distributions with this test of hypothesis also, okay? So that you will get idea of the exam also, final exam also. And please solve it on your own. That is the main thing
Excuse
which
me,
I
ma'am.
require it.
Ma'am, the test will be on which platform?
Yes,
Hello. The test will be on which platform, ma'am? Like Teams or Google Form something?
I will take it in Teams.
Okay, ma'am. Okay.
The test will be in Teams. So the time limit is also there, correct?
Okay.
Will be in Teams. Okay. Okay, so with this, we'll end with this very important thing. So there's only one method which we are going to see it in chi-square distribution, which is normally everywhere we are using it. Okay, so now you send me the attendance on a group. That you do it because I have a lecture, next lecture. So bye to everyone. Meet you in next week.